Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 42 of induction motor chapter. So today we will discuss about power flow of induction machines and torque slip characteristics. Also we will do questions. Okay, so that's why this is the assignment lecture as well. So if you see like previous lecture we stopped here, right? We were discussing about air gap power, rotor copper loss. So today we will dive more deeper into it. So I have drawn this circuit, the equivalent circuit and the physical circuit, right? So if I see initially whatever input power I'm providing input power here, right? First of all, some of it is getting lost in the stator. So my input power P input, some of it is getting lost in the stator. So it is the stator copper loss. So it is, I write it in short, PSCL. Okay, stator copper loss. Then after that there are core losses right here. So minus P core. So this is the core loss. After that, I come to the rotor circuit, rotor side. In rotor side, there will be rotor copper loss. So minus P rotor copper loss. So this whole power, right? This power actually is called as the air gap power, because after adjusting of all the losses like the input, like the stator copper loss and the core losses, after that whatever is present, that is present, like we get the magnetic field right on the core, on the air gap. So that's why that air gap has this much amount of power. Okay, and this, right, is also sometimes called as Pg, because it is the air gap power. Okay, so this is what my Pg is equals to. Pg is equals to, so Pg is equals to this. So this is my air gap power. Now with this air gap power I subtract the rotor copper losses, rotor copper losses, and also this will be my mechanical output power, that is equals to Pm, that is written over here, P mechanical output power. After this what happens, this is a P mech, right? After this the rotor tries to rotate, right? The shaft tries to rotate, and in mechanical as well there are few losses like friction and windage loss. This we have discussed in DC machines, because when the rotor will try to rotate, there is air friction, there is some sort of thing, right? Moving parts are there, so there will be a bit of losses. So we have to subtract the friction and windage loss. Okay, this we have to subtract. After subtracting this, whatever power I get, that is actually the shaft power, that is what you will see. This power is what you will see, that is written over here. So there are so many things, so many losses right inside it. So like so many things are happening inside an induction machine, like what an incredible machine it is, right? So many things are happening. Okay, so this is the actual power that you receive at the output, right? So totally the efficiency, generally we don't measure the efficiency, but efficiency will be P out upon P in, right? So it is basically P shaft upon P in. Into 100%. Okay, so yeah, this is the basically power, I hope you understand. This is known as P shaft, or sometimes this is called as PO as well, PO as well. Now let's discuss about few things which we discussed in the previous lecture, right? About the uh, about the air gap power. What is the air gap power? So what is the air gap power? So air gap power is basically we derived in the previous lecture. I will directly take it from the previous lecture. It was this, right? Air gap power, rotor copper loss, and the mechanical power. So mechanical power is this one, right? Whatever is getting dissipated here. So the P mechanical is this. We derived this in the previous lecture. It is I2 dash whole square, because it is referred to the primary now. I2 dash whole square into R2 1 by S minus 1. The P rotor copper loss. What is the rotor copper loss? It will be the current, rotor current into the rotor winding resistance, that is R2. right? So the air gap power, this we derived in the previous lecture, comes out to be I2 dash whole square into R2 divided by 1 by s. Okay. So this is what my air gap power is equals to. Now remember, all these are per phase. Okay, all these are per phase quantity. So I want to write 3 phase, so I have to multiply 3, right? This also I mentioned in the previous lecture. So don't forget to multiply the 3 because this is a per phase equivalent circuit. In 3 phase, you just have to multiply into 3. Okay, missed out to multiply the 3. Okay. So this is the expression for the air gap power, right? I hope it is clear to you. What is the expression for the air gap power? Okay, this should be dash here actually. It should be dash here. Yeah, missed out a link. I think in the previous here also it should be dash actually. It should be dash. Here as well it will be dash. This will be. This will not be. This will be I2 at S only. Yeah. Okay. Okay. So this is my air gap power. Air gap power. Okay. How can I relate it with the input power? Basically, I want to relate this thing with the input power. So here as well, I have written my air gap power. Air gap power is equals to the input power minus the core losses minus the stator copper loss, right? So we can relate our input power. Input power will be equals to the stator copper loss. So input power, right? Because if you want to find out the efficiency, it will be the stator copper loss. What is the stator copper loss? It is I1 square into R1, correct? Plus the core losses, it will be some constant value P core plus the air gap power. This will be my input power. Okay, I hope this portion is clear. Okay, so now let's discuss about the mechanical portion. How can I derive the mechanical power? Already I have written over here. This is the mechanical power. I want to discuss about the shaft power. What will be the shaft power? So shaft power will be basically whatever is the power, mechanical output power I'm getting here. After that, there are few more components like here, this, right? This friction and windage loss. So this one I have to subtract. Then I will get my shaft power. So shaft power already have derived it. It is basically equals to mechanical power minus the friction and windage loss. Okay, friction and windage loss, right? So basically these are also called as the rotational losses. Okay, these are also called as the rotational losses. So can you tell me what is the torque developed? So what is the mechanical torque? Torque developed, Tm. So developed torque actually will be equals Tm will be equals to the, like we know this formula, right? Omega, like rotor is rotating with a speed of omega r, right? So that is equals to the mechanical power output, because I am just calculating the torque developed due to the mechanical power output. I am not considering the rotational loss. Okay, so if I consider that the mechanical torque developed by the induction motor is simply Pm by omega r, but actually in reality what is happening when the rotor is trying to rotate, there are few rotational losses. So what is the shaft torque? That the torque that I am observing at the shaft, this is the torque that is getting developed, and what is the torque that I am observing at the shaft? Okay, this is the shaft torque, that is PSH divided by omega r, because rotor is rotating with the same speed only. Okay, so this is known as the shaft or the net torque. Shaft or net torque, right? Torque observed on the shaft, and this is known as the torque developed, because the induction motor in reality is trying to develop this much amount of torque, but it is not able to because there are friction and windage loss. So This is the developed mechanical torque. Okay. So one more thing, what are the losses? One more thing I want to discuss. What are the constant and variable losses here? So here the constant losses are what? Again, this actually we have discussed in the machines, DC machines chapter, but I guess instrumentation guys will not understand this, so I will explain. Constant losses meaning they do not vary with the load current. They do not vary with the load. So of course we know iron loss, right? It does not vary with load. It does not depend on the current I2, right? It does not depend on the current, right? Iron loss plus the rotational losses, it is a fixed loss, okay, because whatever air drag there is, right, it does not depend on the load value per se, it only depends on the basically a fixed value. It is a fixed value. Rotational losses are fixed, they do not vary with load current, okay, with change in loads basically. So rotational losses are my constant losses, and what are my variable losses? Variable losses are those losses which depend on the current. So here in this case only one kind of losses are there, that is copper losses, both copper losses both in the stator and rotor. Okay, so these losses will be variable. Okay, so let's solve a question to understand this even better. A 25 kilowatt, so whenever this 25 is given, right, it is talking about the output rated power. So this is the shaft power. Whenever a power rating of a machine is given, if the rating of a machine is given, it is basically means how much power you will be able to observe. So you will be able to observe, if you operate the machine in rated condition, you will be able to observe 25 kilowatt. So basically they are telling you that the shaft power, because that is the output power that I'm getting ultimately, right? So shaft power is 25 kilowatt. Okay, that is simply 25 into 10 cube watts. It is a 50 hertz, it is a 3 phase 50 hertz 4 pole. So P is 4, hertz induction motor operates at a speed of 1410 rpm, right? So NR is 1410 rpm if it is operating in rated condition. Under full load condition, basically it is telling that it is operating in rated condition. The mechanical losses are 850. Mechanical meaning same as friction and windage loss. Okay, so if it is telling basically the friction and windage loss, mechanical losses meaning this only one kind of mechanical loss we have, friction and windage loss. Okay, it is 850 watts. And they are telling me the stator losses are 1.7 times the rotor copper losses. Okay, the stator losses are 1.7 times the rotor copper loss. This is very interesting. So the losses in the stator loss equals to 1.7 times the rotor loss. Now can you tell me what kind of losses are there in the stator? What kind of losses are there in the stator? The losses in the stator, if you remember, is the stator copper loss and the iron loss, right? Those are the two losses mainly. If you go into this block diagram, if you see here, right, what kind of losses are there in the stator? In the stator only stator copper loss and iron loss, coal loss basically. So the same thing will happen over here only. So let me go through, determine the following. Gross mechanical power developed by the motor. What is the gross mechanical power? So for the first portion, the gross mechanical power is very easy, right? What is the gross P mechanical power developed? It will be the basically the shaft power plus the losses, because plus the mechanical losses, right? Plus the friction and windage loss, because that is not like that, the rotor cannot do anything about it. It will develop this amount of mechanical power, but some of it will be lost in the friction and windage loss. Rotor cannot do anything. So the mechanical power developed will be P shaft, that is given as 25 kilowatt, I guess. 25 kilowatt plus friction and windage loss. So friction and windage loss is 850. So this will be 25,850 watts. Okay, this will be the mechanical power developed. This will be the answer of the first part. Let's go to the second part. The second part, rotor copper loss at full load. So what is the rotor copper loss at full load? How do I find out the rotor copper loss? Okay, rotor copper loss. So do you remember anything? I told you one relation, right? I know this relation, that the air gap power is to the rotor copper loss is to the mechanical power output is equals to 1 is to S is to 1 minus S, right? This we have discussed previously, correct? So I will use this relationship. So I know the mechanical power. So basically what I can do is the mechanical power divided by the rotor copper loss will be equals to S divided by 1 minus S. Simple ratio thing, right? So this will be basically P mechanical. P mechanical is 25850. Now what is the slip? I don't know what is slip, right? How do you find out slip? In rated condition, they have given me the speed of the rotor. And what is NS? NS will be 120 F by P. So 120 into F. F is 50 hertz. F is 50 hertz. Divided by the pole. Number of poles is 4, I guess. So it is 4. So it will be basically 13 to 50, 1500. So if I do this right, 1500 RPM, 1500 RPM. Okay. So from here I can find it out what is slip. Slip is basically NS minus NR divided by NS. So it is basically 1500 minus, at rated condition it is rotating at 1410 RPM, right? Divided by NS, that is 1500 RPM. So this will be 90 divided by 1500 RPM. So this will be basically 3 get multiplied 3 divided by 50 basically. This will be the slip. Okay, now I can use it in this relation. So basically my mechanical power is given as 25850 divided by the rotor copper loss, that is what I have to find it out, equals to 3 by 50, 47 by 50, so from here I can easily find out the rotor copper loss. So rotor copper loss 50-50 will get cancelled, so it will be basically 47. Okay, something is off. How is it this much, this high? Slip is a small amount. Okay, I have written it other, like opposite. Sorry, I know you guys were screaming in the comments. I'm sorry, I've written it the other way around. That is what I was thinking. Like, how can the rotor copper loss be so higher than the this mechanical power? How is it possible? Okay, now it is fine. So it will be 3 divided by 47 into 25850. So this comes out to be 1650. So 1650 is the rotor copper loss. From here, can I find out the air gap power? Very simple, right? I can find out the air gap power, but they have not asked yet, so we don't need it. So they are asking what is the rotor resistance per phase given that the full load rotor current per phase is 65 amperes. So I know they are asking the rotor resistance per phase. So if I draw the equivalent circuit, here I have R2, here I have JX2, okay. So this is I2 and they have given me this I2 current to be 65 amperes, right, per phase. I'm just drawing the per phase equivalent now. So per phase it is 65 ampere. So I know what is the rotor copper loss. Remember, this is the three phase rotor copper loss, right? So if I want to write down the rotor copper loss, P rotor copper loss, it will be equals to what? 3 times this I2 whole square into R2, right? So from here I know I2 square, I know 3, I know rotor copper loss. I can simply find out the R2, right? I2 whole square is 65 whole square. So this will be basically R2 comes out 0.13 ohms. Okay, so this is what my R2 will be equals to. I hope it is clear. Now let's move on to the fourth portion. What have they asked in the fourth portion? In the fourth portion, they are asking full load efficiency. For full load efficiency, for full load efficiency, I need to find out the input power. So already stator losses are given to me, right? What is the rotor losses? So rotor losses are what? Rotor losses is the simply rotor copper loss, right? Rotor losses are simply rotor copper loss. So I can easily find out the stator losses. So stator losses, right? Stator losses will be equals to 1.7 into the rotor copper loss. That is the rotor loss, right? Only that is the rotor loss. Basically, other loss is friction and windage loss, right? That is a mechanical loss. So it is 1.7 times 1650. So 1650 into 1.7, it comes out to be 2805. 2805 watts. That is what my stator loss is. Okay, that is what my stator loss is. Now you know one thing, right? What is, like, basically what is the air gap power? I need to find out basically what is the input. Input will be equals to air gap power plus the stator losses, right? Which includes the iron loss and the stator copper loss. Correct? If you remember, if I just copy this flow here, circuit here, right? If you see, so the input power, like this is the air gap power, right? This is the air gap power, whatever I'm flowing in. It is basically like, what is the input? Input is basically combination of this plus the air gap power. Correct? So I will just take this circuit so that you don't get confused. So I can say, what is the air gap power? Do I know the air gap power? Again, I have to use this relationship, right? Again, use this relationship. I know rotor copper loss, so I can find it out very easily. So the ratio of air gap power to rotor copper loss is basically 1 by S. Okay, so I can say that the air gap power Pg will be equals to this rotor copper loss, that is 1650 divided by 3 into 50. So it is basically 27500. Okay, so that is the air gap power. Now I will just add these two values up. So what will be my overall P input, because I have to find out the efficiency, right? P input will be air gap power plus the stator losses, which is basically air gap power is basically 27500 plus the stator losses is 2805. So this will be equals to 30305 watts. So efficiency will be what? Efficiency will be simply P out over P in. So P out is basically P shaft over P in into 100 in percentage. So P shaft is basically the output power, that is 25 kilowatts, 25 into 10 cube, and the input power we have just calculated, it is 30,305. So into 100 percentage. So it is basically 82.5 percentage. Okay, so that is basically the efficiency, that is basically the answer of this question. So like I hope everything is clear now why each and every term is important. So I want you to try out this question now. As I have solved this, I want you to try out this question, and I guess another questions are there. So I want you to try out these questions. I will come back with the solutions. This is another question, please try it out. These are all assignment questions, right? So yeah, I guess this is the last one, or not the last one, this one is the last one. Okay, so try out all these questions. I will come back with the solution. So let's solve this circuit. A 10 kilowatt, again, if it's 10, like they are giving the power, it is a output power, shaft power is 10 kilowatt. Okay, 3 phase 4 pole, so number of poles is 4, delta connected. Okay, it is a delta connected induction motor, draws a no load current of 8 amperes. So delta means stator is delta connected, right? Stator is delta connected, it draws a current of 8 amperes. So in delta connected, right, if it draws a current of 8 amperes, basically what they are telling that the line current is 8 amperes. Okay, line current, whenever they mention any current, right, it is always with respect to line. So line current is 8 amperes. So what will be the phase current? Phase current will be 8 by root 3. Okay, not discussing about that for now. And consumes 660 watt of input power. So basically the no load losses, right, the no load loss, basically when load is not connected, then it is telling that the input power that it takes in no load is 660 watts. Okay, $660. So under full load conditions, the line current increases to 18 amperes and the input power is 11.2 kilowatt. Okay, under full load conditions, the line current is 18 amperes. So under full load condition, like ILFL of the stator is 18 amperes. Okay, under full load condition, and the input power P input under rated condition is 11.2 kilowatts. Okay, the stator effective resistance per phase is 1.2 ohms. So per phase stator resistance per phase, right, is 1.2 ohms, and the friction and windage loss, the friction and windage loss is 420 watts, right? Assume rotor ohmic losses are negligible. What is the stator iron loss? So first of all, what do I know? The no load loss, actually if I draw the circuit, right, no load means the load is open, it is open circuited, that is what no load means. So if I bring the equivalent circuit over here, means load is not connected, right? Load, if load is not connected, this is the load resistance, right? If load is not connected, that means this is basically tending towards infinity. So load is open circuited, that is what no load means. So this is basically open circuited, right? Open circuit. So I2 dash is 0 amperes of current, and they have told me that the stator side takes 8 amperes of current, but remember it is a line current. What is the phase current? This is a per phase equivalent model. So the phase current will be, in case of delta, it is 8 amperes, 8 divided by root 3. Eight divided by root 3. Okay, so this will be the I1 current basically. Okay, so what I can say is that okay, this is done, this portion is done. Now what I can say is what is the no load losses, like what is the power that it is taking. So there are mainly three losses, right? No load, because although the load is open, okay, no load means load is open, but rotor still tries to rotate. In no load there are three kind of losses. One is the this, in no load also this loss will be there, this loss will always be there, right? So here I have the, basically I have, because actually in reality some small ampere some small current will go. Okay, so I will write here the point, the rotor side current will not be 0. Why it will not be 0? Because you know this, right? In no load, if I have no mechanical load connected, the motor rotates in a very fast manner, right? Rotor rotates in a very fast speed, right? So basically in no load, my NR is almost is tending towards NS, right? But still it will be very near to 0. Basically NS minus NR will be very near to 0, but it will not be exactly 0. So still there will be some slip, and due to the slip what will happen, there will be some induced EMF in the rotor side, E induced, E2S, and due to this some current will flow, but that value of the current will be very low, because what is my E2S equals to? E2S is equals to root 2 pi S into F, right? S into F, okay, S into F into this N2 into KW2, right? And phi also is there, okay, phi also is there. So the thing is that this S, right, okay, NS minus NR will be very near towards 0. Okay, yeah, NS minus NR will be very near towards 0 because they will not be very high relative speed. Then what will happen? Then basically I know what is slip. Slip is equals to NS minus NR divided by NS. Okay, so this will be tending towards 0. So this induced EMF will be very low, right? Induced EMF will be very low. So if induced EMF is very low, the current also, like some current will be there will be some flux cut, right? So this will not be entirely infinity, this will have some high value, this will be high value, okay, because this is tending towards 0. So there will be some rotor current, but it will be almost negligible. But since the rotor is rotating, it is not completely no load, meaning like let's assume this is the shaft, I am not connecting any load, that's it. No load meaning I'm not connecting any load, right? Load is not there with the motor, I'm not connecting any mechanical load like a pump or stuff, right? But the rotor will rotate without any load, so there it will take some current, but that current value will be very very low. Okay, so that is the thing here. So ultimately what do I mean? So there will be some friction and windage loss, because you might have a confusion in no load, how is there friction and windage loss if the motor is not rotating? Motor is rotating, right? But mechanical load is not connected, like a pump or something, it is not connected there. Okay, so this will be, so here I want to comment that at no load basically means mechanical load won't be connected. mechanical load won't be connected. Okay, but rotor will still rotate very close to ns. So nr will be very close to ns. So that is the thing that we want to discuss. So like thing is, there are actually four kinds of loss. This will not be exactly equals to zero. This will be tending towards zero. So there are four losses. First one, first of all, current is going through the stator. So there will be stator copper loss. Plus I have this component, right? What is this? Iron loss. Plus I have now the rotor copper loss. Rotor copper loss. Plus the friction and windage loss or the mechanical losses. Okay. So the thing over here is this will be very low. Very low. Why? Because the rotor current itself is very low. It will be very low. Okay. Hence, we can ignore it, right? And anyways, we will not be able to find this value in this question. We will not be able to find this value. So anyways, we have to ignore it, right? That is the first point. Now, I know the no load loss. Do I know the stator copper loss? Yes. I know the current through the stator. Per phase stator copper loss will be what? So per phase stator copper loss. This will be 3, sorry, 1, or if I directly write stator copper loss, it will be 3 because per phase will be I1 whole square, I1 per phase whole square into the stator resistance R1, right? So it is 3 into I1 per phase. I1 per phase is 8 by root 3 whole square into R1. R1 is 1.2, right? That is the stator resistance per phase. Okay. So this is the stator copper loss basically. And I like basically in the first portion, right? I have to find out the iron losses. I know the stator copper loss. From here, I am ignoring the rotor copper losses. So only these two are these three are present, right? So no load loss. So if I write the equation 1 again, if I want to write the equation 1, so if I want to write the equation 1, what I can say is the no load loss, right, is 660. Stator copper loss is 3 into 8 by root 3 whole square into 1.2 plus the iron losses. This I don't know. This I have to find out. Iron losses I have to find out. And rotor copper loss I'm ignoring, right? So from here I can find out the iron losses. So this value will be equals to basically, if I want to find out this value will be okay, 3 will get cancelled. 64 into 1.2 subtracted by 660. Okay, sorry, friction and windage loss also is there, right? That is 420, I guess. That I missed out. Friction and windage loss. Yeah. So 660 minus 76.8 minus 420. Okay. So it is 163.2 watts. Okay. So the coal loss or iron loss is 163.2 watts. This is the answer for the first one. Okay. So this is the answer. Right. Let's solve the next one. Let me solve the next one. So in case of next one, if I want to find it out, in the next one. So the next one is basically the total rotor losses at full load. So what is the total rotor losses at full load? How do I find it out? Okay. So I can find out the total rotor losses at full load, because rotor losses will be the rotor copper loss. That is what they are asking, right? Total rotor losses will be the, basically they are asking the rotor copper loss, correct? So total total rotor loss will actually include the rotor copper loss plus the friction unwinding. Okay, sorry. So rotor loss at full load, total rotor loss at full load will include the rotor copper loss plus the friction and windage loss. Okay, so uh, how do I find out the rotor copper loss? Actually, there is no other way to find out the rotor copper loss without knowing the rotor resistance, but they have not mentioned, so I will not be able to find it out. Friction and windage loss is constant, that I know. So I can go other way around. I can find out the air gap power, right? What will be the air gap power? So air gap power will be equals to the input power at full load minus the stator copper loss, or the stator copper loss and the iron losses, right? Now, do I know the input power? Yes, actually they have provided me the input power at full load and the line current at full load also they have provided me. So these two information actually very conveniently they have provided me in the question. So I will utilize that. Okay. So basically input power I know, that is 11200 minus the stator copper loss. So line current is 18 amperes. What will be the stator copper loss? It will be 18. So basically it is per phase, so I have to multiply 3 first of all. 18 divided by root 3, that this will be the phase current whole square into the stator resistance, that is 1.2, minus the iron losses. Iron losses I have just found out in the previous part, 163.2 watts. 163.2 watts. So this will be equals to, if I write down the values over here, uh, 18 whole square into 1.2 plus 163.2 plus 11200. So this comes out to be 10,648 watts. Okay. So this is the air gap power basically, right? So from here, will I be able to find out the copper loss? Yes, we know this relation, right? Air gap power to rotor copper loss to the mechanical power. This ratio is basically 1 is to S is to 1 minus S. This will be helpful in so many places, trust me. So I know what is this, Pg upon P rotor copper loss, that is what I have to find out, is equals to 1 upon S, right? So Pg is equals to 10,648 divided by rotor copper loss. Rotor copper loss is, I have already found, I don't know, but that is what I have to find out. Rotor copper loss equals to, now what is slip? So okay, I don't know what is slip. Have they told me the speed at full load? draws 4 pole 10 kilowatt. Okay, speed is not told to me. How will I find out the slip? Filter connected 10 kilowatt. Okay, how do I know the? Okay, okay, actually speed is not given. Speed should be given, I guess. Then else how will I find out the slip? uh okay, one more information, one very small information. The shaft power at rated voltage, I mean rated condition is given, right? Okay, this is what I missed out. This is given, right? Shaft power at rated condition. So what is the mechanical power? So they have given me, like this also I have missed out. So the shaft power they have given me, right, at rated condition is 10 kilowatt. So what will be the mechanical developed power? It will be basically the shaft power plus the friction and windage losses, right? Because I have to add that, that is additional loss. So 10 kilowatt plus what is the friction and windage loss? It is 420 watts, right? 420. So it will be 0.42. So this will be 10.42 kilowatts. Okay. So I can directly say that my rotor copper loss divided by 106148. So like, okay, I'm stuck here. I don't know the slip. So how will I use it? I will now use this relationship. So this will be PG divided by Pmec equals to 1 divided by 1 minus S. So from here I can directly find out, I know PG, right? I know Pmec. So I will be able to find out what is 1 minus S. 1 minus S will be Pmec upon PG. Pmec is 10.42 kilowatts and PG is 10.648 kilowatts. So from here I will be able to find out the value of S. So into 10 point, okay, 10420 plus 1, so 0.0214. Okay, that will be the value of the slip, right? Slip will be 0.0214. Okay, I have found my slip. So from here I can find out the rotor copper loss. So rotor copper loss will be equals to this slip 0.0124 into this value 10 air gap power, right? So it will be 10,648. 10,648. So this value comes out into 10,648. So it comes out to be 228. So 228 is the rotor copper loss at full load. Okay. So what is the overall rotor losses? So total rotor losses will be equals to the rotor copper loss plus the friction and windage loss. Okay. So rotor copper loss is 228 and friction and windage loss is what is friction and windage loss? 420 watts, right? That is 420 watts. So this plus 420 is 648 watts. Okay. So this is the basically the total rotor loss that I am able to find out. Okay, this is the answer for the second portion. Like the question is going bit lengthier than I expected. Okay, I think we have to extend the torque slip characteristics in the next lecture. Okay, so Okay, this is the rotor copper loss. Now, uh, okay, total rotor loss I have found out. Rotor copper loss at full load already I have found it out, so it is already done. So the rotor copper loss at full load, right, at full load will be equals to 228 watt, already found, right, already solved for it. So the fourth portion is speed of the motor under full load. Speed of the, now what is the speed of the motor under full load? I know the slip value, right? I have already found out the slip is this value, correct? Slip is this, so I will be able to find out nr. So basically I know the formula for slip, s is equals to ns minus nr divided by ns, right? So what is nr basically? So nr is basically 1 minus s into ns. That is what my nr is equals to. So 1 minus s, right, it is 1 minus 0 point whatever this value is there, 0.0124 into ns. Ns is how much? Ns have I calculated? No, ns is basically, it is a 4 pole machine, right? 4 pole 50 hertz machine. So ns will be 120 into 50 by p, so 120 50 by 4, so this is 1500, right? So basically nr will come out to be 0.0124 plus 1 into ns. Ns is 1500, so it is 1481 0.4 rpm. So this will be the rotor speed basically. Now next, the last one, I guess, last one is the internal torque, shaft torque and efficiency at full load. So internal torque basically means the developed torque of the motor, right? So basically they are asking the T mechanical developed torque, because friction winding, excluding the friction and windage loss. So T mechanical is the internal torque, that is basically equals to P mechanical upon the speed omega r. So what is P mechanical? P mechanical is here, this one. P mechanical is this one, right? 10.42 kilowatts. So it is 10,420 into 2 pi into rotor speed. Rotor speed is this 1481.4 divided by 60, right? So into 60 divided by 2 into pi into 1481.4. So it comes out to be 67.16 Newton meters. SI units is Newton meters. 67.169 Newton meters. What is the now next, what is the shaft torque? Shaft torque will be P shaft upon the omega r. Already I know what is the shaft power, right? Shaft power is 10 kilowatt as mentioned, right? As mentioned, it is operating in rated condition. So shaft power will be 10 kilowatts. Divided by omega r. So omega r is this value, right? Same value. I will copy and paste. So this is 10,000 into 60 divided by 2 into pi into 1481.4. So it comes out, it will be obviously less because I am excluding the friction and windage loss. So it comes out to be 64.46 Newton meter. Okay, this is what the shaft power is equals to. What is the efficiency? Efficiency, right? Efficiency is simply P in upon, sorry, P out upon P in. So P input already is given to me, that is 11.2 kilowatts, right? It is given to me at full load. The input is 11.2 kilowatts, output is 10 kilowatts. Very simple, right? It is simply 10 kilowatts upon 11.2 kilowatts into 100. So it is 89.286%. Okay. So yeah, this is the answer basically. These are the answer. I am sorry, this question became a bit lengthier than I expected, but I guess it's fine. I guess we like most of the concepts are clear. So yeah, that's a good thing. So now let's move on to the next question. It's a gate question, so it will not be this lengthy, okay? But those concepts will be used. So a 400 volt 50 hertz 30 horsepower. So okay, one more thing. This is the rating, right? Rating of the motor. So one more relation you have to remember, right? The conversion between horsepower, the conversion between the horsepower and the what do you call kilowatt, right? So do you remember the conversion? So basically, 1 horsepower is 735 kilowatts. Okay, I will still check it. Okay, I will Google it because I also have forgotten. I have not used it. 1 horsepower 2 kilowatt. How much is it? Yeah, it's yeah, this only 735.5. So 735, not kilowatt, sorry, watt. 735.5 watts. Okay, this you have to remember. Okay, so this is the rating. So whenever they are giving the power, right, rating means the output. Rating, this we have discussed in DC machines, right, for electrical guys. Rating means the output power, rated output power. Okay, three-phase induction motor is drawing a 50 ampere current at 0.8 power factor, right? So it is drawing a current of 50 ampere. So basically the stator is drawing, it is a, have they told us whether it is star or delta connected? Okay, they know where it is mentioned whether it is star or delta connected, so I will assume it to be star connected. Okay, so assume star connection, assume star connection. In star connection, the line and the phase currents are same. Assume so the stator current will basically be equals to, stator current will basically be equals to they have given me in rated condition it is 50 ampere at point a 400 volt. Okay, this, right, they have not told me whether it is operating rated or not, I don't know. Okay, so I'll just write the stator current is 50 ampere at 0.8 power factor. Power factor is 0.8, lag obviously. The stator and the rotor copper loss is, okay, stator copper loss they have given me, stator copper loss in this same load, right, is 1.5 kilowatts, so it is 1500 watts, and the rotor copper loss is 900 watts. The friction and windage losses are 1050. Friction and windage losses are 1050. Okay, coal losses are 1200. The air gap power of the motor will be what? So they are asking me the air gap power. I don't know what is the input power. Okay. They have also not mentioned about. Okay. Okay. What will be the air gap power? I don't know even, I even don't know the speed. Okay, nothing I know. Okay, one thing I know, this is the input current. So what is the input power? Can I find out the input power? Three phase power. Input power will be what? It will be root 3 into VL into IL cos phi. Cos phi is given, IL is given, VL I know the line voltage. So everything is known here. So I know the input power. So input power will be root 3 into 400 into IL. What is IL? IL is this current, right? 50 amperes. I don't know whether it is rated or not. I don't even have to know. So it is into 50 into the cos phi, that is 0.8. So this will be equals to what? This will be 400 into 50 into 0.8 into root 3. So 27712. 27712.813 watts. Okay. 277.27712.813 watts. Okay. So this is the input power. I need to find out the air gap power. What will be the air gap power? It will be basically the input power minus the stator copper loss minus the iron losses. So input power is 27712.813 minus the stator copper loss. Stator copper loss is 1500 watts minus the iron loss is, or coal loss is 1200 watts. So this comes out to be minus 1500 minus 1200 divided by 1000. Want to write in kilowatts. So 25, almost 25 kilowatts, 25.01 kilowatts. So it comes out to be 25.01 kilowatts. So this will be the answer. Okay, that's how simple gate questions are. Okay, compared to this question, I hope this is much simpler for you, right? So let's now solve this one. Okay, this question. So here if I see a 3-phase 50 hertz 4-pole induction motor operates with a slip of 4%. Okay, so slip is 4%. So it is 0.04 basically. Rotor resistance, pole is 4-pole machine, right? 4-pole machine, and frequency is 50 hertz. Okay, resistance, that is R2 is 1 ohms, and the standstill reactance. Okay, so X to S is the standstill reactance is 4 ohms when the slip is 1. Okay, so calculate the percentage reduction in power factor as the motor goes from running conditions to standstill. Okay, so what is the power factor in standstill? So let me write cos phi s in standstill. So cos phi s in the case 1, so I will write the case. So case 1 under standstill condition. Okay, in standstill condition case 1, the rotor is not rotating, right? If rotor is not rotating, NR is 0. If NR is 0, what is the slip? Slip is equals to NS minus NR divided by NS. Okay, so I can say that NR is 0, so slip is 1. So basically it is, how do I find out the power factor? Cos phi is what? Cos phi is the power factor. How do I find out the angle? So angle, right? Phi 1 angle will be what? It is basically a inductive circuit, right? So it is X to S and R2. So basically it will be, what will be the phi 1? Phi 1 value will be tan inverse R2 upon X to S. R2 upon X to S. So this comes out to be equals to So tan inverse R2 upon X2S. So R2 I know already, right? R2 is 1 ohms and X2S is also 1 ohms, right? Sorry, 4 ohms. So sorry, I have written it the opposite way around. It is X2S upon R2, right? Okay, so tan inverse force. So 75.963 is the angle. So what will be the power factor? So I have to do cos of this. So cos of this will be 0.425 okay. So yeah, power factor will be this in the case 1. What is the power factor in the case 2? When the rotor is in running condition. In case 2, right, when the rotor is running, they have already given me what is the slip frequency. Sorry, slip, right? Slip is zero point 0.4, I guess, or 0.04, sorry, 0.04. 0.04. Okay, so slip is 0.04. So if slip is 0.04, then I know this, right? What is actually reactance? The rotor reactance, it is 2 pi into S F into L2, right? So in standstill, what happens is this becomes basically S is becoming 1, right? It becomes 2 pi L2, right? So I can, what I can comment is if I find out the ratio of x2 upon x2s, it will be what? It will simply be S. So basically my rotor reactance in the second case, because S was 1 previously, that's why it did not change. It is S time x2s, right? So S this time is 0.04. So x2s is 4. So this will come out to be 0.16 ohms. Okay. Can you imagine how much, like how huge of a change this is, right? Let's see how much the power factor changes. Okay. So now the angle, right, in the second case, it will be tan inverse x2 divided by r2. So this will be equals to basically x2 divided by r2. x2 is 0.16 and r2 is 1 only, it does not change. So tan inverse this, it is very low, right? 9.09 degree. So what is the power factor? Power factor will be cos of phi 2. So if I do the cos of this, right, it becomes 0.987. So can you imagine how big of a difference this is, right? So what is the percentage, like, so what they're asking? They're asking the percentage, calculate the percentage reduction in power factor as the motor goes from running conditions to standstill. So it is going from running condition to standstill and already they have shown me reduction. Okay, why is this important? Why understanding that they have asked reduction is important? I will explain just in a second. Okay, so they are asking the percentage change from running condition, running to standstill. So this is what this is basically. So from running to standstill, so running is a reference, so it will be the new power factor minus the old power factor divided by the old one relative to the old one, right? So cos phi 2 is the running one, that's why I'm calculating the change with respect to the running one, okay, into 100, obviously 200 the percentage. So this will be equals to cos phi 1 is basically 0.2425 minus 0.9874 divided by 0.9874 into 100 percentage. So this plus 0.242425 divided by 0.9874 into 100. So it comes out to be minus 75.44 percentage. Now the important fact is negative is coming. Negative signifies what? Negative signifies reduction, right? And already they have asked me what is a reduction. So I don't need to write minus. My answer should not be negative, right? It is a NAT type question, so answer should not be negative. It should be answer should be 75.44 percentage, because already they have mentioned in the question itself that they are asking reduction, so they know it is reduction. So I don't have to write here the negative sign to signify that this is reduction. They have already asked me reduction, so I will just write down directly the percentage 75.44. This will be my answer. So I hope that doubt is clear. So let's now move on to the next question. So next question is this one: a three-phase star connected induction motor has a rotor resistance of 0.05 ohms and the standstill reactance is 0.12 ohms per phase. The stator resistance is almost negligible. The EMF induced between the slip ring terminals at standstill, so E to S, right, is equals to 100 volts line to line between the slip ring terminals. I don't know how are the slip rings connected. Maybe it is star connected. Okay, 100 volts line to line when S is equals to 1 because it is standstill. Determine the rotor current. Okay, I have to find out the rotor current and the phase angle between the rotor voltage and the rotor current at a slip of 4%, that is S equal to 0.04. Okay. So phase angle is pretty easy, right? Phase angle is pretty easy. Like this is my rotor circuit, right? This is my R2 and this is basically my S into X2S, just proven in the previous question. So phi 2 will be equals to what? Tan inverse Sx2 divided by R2. So Sx2, right? S is 0.04, X2S, Sx2S, right? Sx2S. X2S is 0.2, so it is tan inverse R2 is 0.05. So basically 0.04 divided by 0.05 into 0.12. So tan inverse of this. So phi 2 comes out to be 5.483 degrees. So they are asking the power factor, right? Okay, they are asking the phase angle only. So phase angle is easy. It comes out to be this 5.483 degrees. Okay, this is the phase angle basically. Now what is the how do I calculate the rotor current? Okay, how do I calculate the rotor current? So rotor current is again okay. I know the EMF induced between the slip rings, right? I know the EMF induced between the slip rings. Okay, at standstill. Okay, basically what are they telling? That the standstill reactance here is given. Standstill EMF induced is given. Actually, this is what? This is line to line, right? But it is like nothing is mentioned. Like here, it is mentioned star connected. Maybe they're talking about the stator. For rotor, it is not mentioned whether it is star or delta connected. I will assume it is star connected. So if I assume it is star connected, then this will be the EMF E2 by root 3, right? Now what is E2 actually? If you remember properly, what was my E2 formula? E2 formula was 4.44 into S into not root 2 into pi into phi into S into F into N2. That's it, right? These are the components. We have 5 components. N2 into the winding also as well. So these are the 5 things. 1, 2, 3, 4, 5. Yeah, winding factor. So they have given me the standstill voltage, right? What is the standstill voltage? E to S, standstill, right? It is when S equals to 1. So they have given me this as 100 volts. Okay, when S is equals to 1. So now can I find out the ratio? So this is basically equals to what? This is equals to root 2 when S is equals to 1, root 2 pi phi, flux will be same, S is will be 1, F N2 into Kw2. So E2S divided by E2 equals to, it is basically, the ratio is simply S slip, right? It will be 1 by S basically. So E2 will be S into E2S, same like reactance. So E2S is this, S is 0.04, so into 100 it will be 4 volt. Remember this is line to line, okay, but for phase it will be what? 4 divided by root 3. Okay, so it will be 4 divided by root 3. Okay, why is it here? Okay, it's for some other purpose. Okay, 4 divided by root 3. Okay, so now okay, so I need to find out the current. So what will be the current? I2 will be simply what? It will be 4 divided by root 3 divided by the magnitude of the impedance, that is R2 whole square plus X2 whole square. X2 whole square is this, right? What is X2? X2 this time is S into this, so it is 0. It is a very low value, it will be almost negligible, whole square. So R2 is 0.05. Okay, R2 is also very low value. Okay, so this is basically, so okay. So this will be 0.04 into 0.12 whole square plus 0.05 whole square whole under root into, okay, 4 okay, this went away, 0.05 whole square, so okay, 0.04 into 0.12 whole square plus 0.05 whole square whole under root this into 4 divided by root 3. So it comes out to be 45.97, almost it is 46 amperes. So I2 in running condition comes out to be 46 amperes. Okay, so is that only the what have they asked here? That is only what have they asked. So rotor current is 46 amperes. This will be the answer. So with this basically we will end today's lecture. We will not do the torque slip characteristics. In the next lecture we will do the torque slip characteristics. Also we will do the testing of induction motors. Okay, so I hope you have enjoyed this lecture. If you did, make sure to hit the like button, make sure to comment down below whatever you felt about the lecture, and I will meet you in the next lecture. Until then, happy learning.